All right. So our plan, what we've done so far, has been to use the limit definition. Limit is h goes to 0 of f of x plus h minus f of x all over h. Or the alternate definition, the limit is x goes to c of the difference quotient f of x minus f of c, all of this over x minus c. And this applies to all functions everywhere. For any function, its derivative can be computed by either one of these two things. And then from here, we use this to create derivative rules, such as the sum rule, quotient rule, etc. And this allowed us to compute derivatives for polynomials and for rational functions. And that's as far as we've got. What other kinds of functions are there out there? Exponential functions we haven't done yet. What else? Trig functions. Log functions. I'm trying to remember, Peter. Were you here for the testing problem?
Yes.
Okay, good. All right. So you know if I need to send you down there. So we have still a lot of families of functions to go. And this week we're going to focus on some tools that are useful for finding derivatives of piecewise defined functions. Functions that are defined in terms of pieces.
Wait, all this week is just derivatives for functions?
Today, tomorrow, and then what's going to happen going into Thursday, we're going to find out how to do derivatives on the calculator. We already sort of know that, but we're going to become official on that. And then on Friday, we are going to, we're also going to be discussing what happens when a function doesn't actually have a derivative. Yes?
I have a question, another question about piecewise functions. I thought we already, like, I mean, we didn't go into depth, but I thought it was just, like, finding the derivatives of each part.
Great question. Yeah. So actually, let's take an example, and then we're going, I will introduce the tool for today, which is the decided derivative. So to get at this, our goal for the next few days is to be able to handle piecewise functions. And our kind of model problem here is going to be f of x is equal to no. Now we've seen this function before, but if you're not sure, go ahead and graph that function. In your notes, just graph the function. And if you can come up with a different name for it. Yeah, it's the absolute value of x, that's right.
Question.
Yes.
So can you have f of x equal to negative x while x is smaller and or equal to 0, like have an equal sign on both?
Well, if I did that, then something interesting happens. There is the potential possibility, he's asking, what if I put an equal sign right here, what would happen? Yeah.
Well, then x could equal to 0, and negative x would equal to 0 on both sides, and then it would be 0 over 0.
Aha. So here, there's the possibility, the potential for a conflict in definition, right?
Yeah.
Because I could have f of x having two different values. But because of the particular way that f is defined, it takes a value of 0 for both pieces, and as a result there is no conflict, there would not be a problem with doing that for this particular thing. Let's generalize. What's true about f at x equals 0 that causes there to not be a conflict? Yes? What's true about the graph of this particular function? Yeah.
Limit as it goes to 0 from the right equals the limit as it goes to 0 from the left.
Yes, and also is equal to the function value. What do we call functions like that? That's right, it's continuous at x equals 0. So if my function is continuous at the joint, then I can include the joint on both sides. But if my function were discontinuous, for whatever reason, then I would now have a function that had a, quote, function that had two values at the joint, and that's not possible. That's not a function anymore.
Okay. Yeah, I'm saying like for this particular one, you want to be like more descriptive and detailed about and do that.
Yeah, it doesn't change a thing if I include the equality here because my function is continuous. It's an interesting question. So now we're going to take derivatives here. And as Heidi suggested, for the vast majority of x's, we're just going to take the derivative of each piece. For instance, if x is equal to 1, then it's really obvious that the slope of the curve here is just the derivative of my function applied at x equals 1. So if I want the derivative f prime for x's, generally speaking, then I'm going to consider all of the x's in this interval. But right when I get to the joint, that's where the problem starts. This is why piecewise functions require special care and feeding. For the point x equals 0, in any neighborhood of x is equal to 0, points to the right are values of x, but points to the left are values of the opposite of x. And so my function is not actually represented by either piece right at the joint. Do you see that? It's a two-faced function. It looks to the right, it sees one piece, it looks to the left, it sees another piece. So, for any x that is greater than 0, it is obvious that my derivative is 1. And for any x that is less than 0, it is obvious that my derivative is -1. But what happens at 0? For that, we are going to have to introduce a new concept, and that is a right-hand derivative and a left-hand derivative. So this is our new thing for today. Let's define a derivative from the right, f prime plus.
Is that the joint?
Uh-huh. Right at the joint where the two pieces come together. F prime plus at c is going to be the limit as x goes to c from the right of f of x minus f of c over x minus c. Notice that I'm using the alternate definition of the derivative, but I'm considering the limit only from one side. So the picture here is that I'm going to go to x equals c, in this case 0, and I'm going to draw myself secant lines that connect those 2 points, and then I'm going to let x approach c, but only from this side. And when I do, I will get the slope of the curve only on this side. And that slope, in this particular case, is pretty obviously +1, right? We can see it from the graph. But let's actually see it analytically for our example. We would say that f prime plus of 0 is the limit as x goes to 0 from the right, as x goes to c, of the absolute value of x minus the absolute value of 0 all over x minus 0. And we've seen this limit before. As x goes to 0 from the right, the absolute value of x divided by x gives us the same value for every positive x, which is positive 1. And so this derivative from the right is equal to positive 1. And now the derivative from the left, we're going to define in a similar way. We're going to say that it's the limit as x goes to c from the left of f of x minus f of c over x minus c. And again, if I come back to my curve here, now I'm talking about going to c, and now choosing x's that are to the left of c, doing a secant line between them, and letting x approach c from the left. Does that make sense so far? And in our particular case, we would say that f prime from the left at 0 would be equal to, set it up for me. What's it going to look like?
Limit as x goes to 0, negative, and negative side of the left. X prime, an absolute f of x minus absolute 0 over x minus 0.
Yes. Notice that it is the same quantity that I'm setting up here. It's f of x in both cases. But the difference is that I'm approaching from the left. And so now when I simplify it, then I get this limit. And because I'm approaching from the left, the absolute value of x is going to be equal to the opposite of x. That's that other piece, right? Which gives us now negative 1. Now, what does this mean? Here's what this means for us. This means that my curve has one slope, one rate of change going in this direction, but a different slope, a different rate of change going in this direction. We know enough about limits to see what this means. This means that if I take the limit as x goes to 0 of this guy right here, which is equal to f prime of 0, then we would say that because the limit from the left and the limit from the right are different values, the overall limit does not exist. That's right. Which means that f prime of 0 actually has no value. There is no rate of change for the curve because that absolute value curve comes in and it has, tomorrow we can call that a sharp corner. Right there. One rate of change this way, different rate of change this way. There is no overall rate of change. Yes?
So the absolute, if it was just the absolute value of 0, does that exist?
Yes, absolutely. It's 0.
Okay.
Yeah. Go back to what absolute value of x is and answer your own question. When x is 0, the absolute value of 0 is x, which is 0. So this is the model for understanding how we deal with piecewise functions. We take the derivative of each piece, yes, but right here at the joint, right when x is equal to 0, we do not assume that this piece will have a derivative at the joint. Instead, we will check the joint separately by looking at the directional derivatives. That's how we're going to handle piecewise functions. See, I gave away the rules. Okay. So this is really our slogan for piecewise functions. Check the joint separately. Okay. Now, I would like to let you guys practice with one. And go ahead and find the derivative f prime of x for all x's except x equals 1. While you do that, I'm going to set up for a graph of our function. Okay. And here's our graph. And what do you get when you take the derivative of the function, Justin? Less than, greater than, he wasn't paying attention. Less than 1. You must check the joint separately. You may not assume, never assume that the joint, the equality will carry down. Because right here, when x is equal to 1, at this point, right here, my function is a two-phase function. It is 2x minus 1 to the right, and it's x squared to the left. You see it? All right. Carry on. What's the derivative on the other side? Mm-hmm. Yep, that's it. That's all I asked you to do so far. Come on. Okay, now what happens at x equals 1? We have to consider derivatives from the right and derivatives from the left separately. So let's set those up. First of all, set up the derivative from the left. Go ahead and do that. First of all, our form. And the form should be the limit as x goes to 1 from the left of the piece that applies when x's are less than 1. That's this guy. So we would have x squared minus 1 over x minus 1. Did everybody have that? And now that limit should be fairly easy. Go ahead and evaluate it. Go. And you should have found that cancellation is the winner here. And so we get the limit as x goes to 1 from the left of x plus 1, which is equal to 2. And so this is our value of the derivative from the left. And what this means is that as I am approaching from this side, right here, going towards 1 in this direction, my curve has a slope of 2. Which actually is kind of hard to draw because my line has a slope of 2 as well. All right, now what about from the right? The right is going to be very similar to this. We're going to compute the derivative from the right as the limit as x goes to 1 from the right of f of x minus f of 1 all over x minus 1. But now we have to be careful about two things. First of all, we have to be careful about which piece we're going to use for f of x. Which piece are we going to use for f of x? Going back to our f of x, because we're looking to the right, we have to use the piece that is defined for x is bigger than 1. That piece is 2x minus 1. This is the key point. I've got one piece for x is less than 1, a different piece for x is greater than 1. I have to use the piece for x is greater than 1 because I am approaching from the right. But now here's the second place that we have to be careful. And that is that I have to use the value of f of 1 in both pieces. Please notice that f of 1 is the exact same quantity for both forms here, which means that I need the value that f has when x is exactly equal to 1. And for that, I have to use that piece right there. F of 1 is 1 squared in both the left-hand and the right-hand derivatives. Does everybody see what I'm saying? Now, does it matter here? Even if I accidentally use this piece, I would still get the same number because my function is continuous, right? So if my function's continuous, if you mess up, it kind of doesn't matter. But we'll see in just a second that if my function is not continuous, it matters a lot. So here, f of 1 is 1 squared, just like it was up here for this piece. So this was the tricky piece because f of x was 2x minus 1, but f of 1 was 1 squared. Do you see what I'm saying? Yes.
Well, why is that 1 squared?
Because when x is 1, f of x is x squared, which is 1 squared. It's not a hard thing, it's not a tricky thing, I'm just reading the language really carefully. Does that make sense? Yeah. Okay, and so now simplifying this, go ahead and simplify it. You can do the limit easily enough. Breaking through, Captain. And you should be able to do an easy factorization to get 2 as that one. Now, if you take a look at what we have here, what we have is that the derivative from the left is 2, and we also have the derivative from the right is 2. So if I were to consider the overall derivative, what value must it have? 2. That's exactly right. So in contrast to our absolute value of x, this piecewise function had the same slope from both sides, and therefore its overall slope at 1 is that value, which is 2. So we would conclude, therefore, that f prime of 1 is equal to 2 because the derivative from the right is 2, and the derivative from the left is 2. So if we were to come back now and evaluate f prime of x, we would say that it is equal to 2x for x is less than 1, and 2 for x is greater than or equal to 1. And if I wanted to put the equality here instead of here, Peter, I could do that just as well, because I get the value of 2 no matter which one I put. Does that make sense?
So is it okay if you just like plug in 1 for the x in that for the I don't know what to call that. Yeah, if you plug in f equal I don't know x equal to 1, so 2x will be equal to 2, right?
Ah, that's an interesting question.
And then it's just kind of easier way to check it.
Okay, so let's come back here, and I think what you're asking is, could I have short-circuited this process by just noticing that I get 2 when x is 1 and 2 when x is 1, so they're equal, ta-da!
They exactly mean like the same thing.
As it turns out, and weirdly, no.
Why not?
And now I'll show you the thing that can go wrong and why we have to do such an arduous process right at this point. But then I'll come back and kind of give you some, modify what I'm saying. So currently, our procedure for piecewise functions is take the derivative of each piece, but the results only hold on the interior of each piece, not at the joint. Then, at the joint, I have to take derivative from left and right separately. Now let me show you why by modifying this function just a little bit. Let's consider a third piecewise function. Let's have h of x equals x squared plus 1 for x's less than or equal to 1, and 2x minus 1 for x's greater than 1. I think all of you can see that the only difference between this function and our previous one is that this piece has been raised by 1. Okay? Now before we get going, I'd like for you to sketch a graph of this piecewise function. And then after that, go ahead and find the derivatives of the pieces. Yes, sir. 1 second. It's x squared plus 1 for x is less than or equal to 1. So hopefully your graph looks just like that. Notice that the red portion, the line, has an open circle at x equals 1. And the quadratic portion, the parabola, the blue part, has a filled-in dot at x equals 1. Does that look that? Okay, good. Now, if we do the derivatives of the pieces, then we find out that h prime of x is equal to 2x for x is less than 1, and 2 for x is greater than 1. And that's pretty easy as well, right? Adding that plus 1 to my quadratic portion didn't change its rate of change or its slope. It just changed where it was vertically. And now, Peter, if we were to use your concept, then we would plug in x equals 1 here, x equals 1 here, and we would get a slope of 2. We would say that my curve has a slope of 2 right at this point. But looking at that curve, that really disturbs us. because right at x equals 1, it's not at all obvious to me that this curve has a rate of change 2. In fact, it looks kind of funky to me, doesn't it? So let's find out by checking the directional derivatives at x equals 1. And so here we go. First of all, we take the derivative h prime minus for h prime from the left at 1. Everybody give me the form. That would be the
Like when as x goes to one from the left side, f of x minus f of 1 over x squared.
very good, except it's h. But other than that, we're good. All right, and now we're going to go fill in values. For h of x, because I'm going from the left, I'm going to take the piece that applies when x's are less than 1. And that piece is x squared plus 1. Just like that. And for h of 1, I'm going to come back and I'm going to use the piece that applies when x is equal to 1. And that piece is 1 squared plus 1. If it helps you, and I think it does help students, before you get computing, compute what h of 1 is equal to. What is h of 1 equal to? 2. Right. And so that value is the value that you're going to use for h of 1. Because if h of 1 is 2, then gosh darn it, h of 1 is 2. So we come back, and we compute like so. And now all of you should be able to find this limit. Go ahead and do so. This one is not going to surprise us. And all of you should have gotten 2 for that limit. Easy. But now we consider the derivative from the right, and something strange happens. Of course, the derivative from the right is going to be the limit as x goes to 1 from the right of everybody. What is it? Everybody nice and loud.
H of minus 1 over x minus 1.
That's right. And for this piece, what is h of x?
X squared minus
2x minus 1. Wrong piece, wrong side. 2x minus 1. And what is h of 1? Notice I did not say for this piece what is h of 1. What is h of 1 as defined?
X squared plus 1.
Do we have a value for it? 2. We computed that value right up here so that we would not lose track of what it is. It is 2. And now something very strange happens, and this answers Peter's question. We get the limit as x goes to 1 from the right of 2x minus 3 over x minus 1. Do you see something that is unusual about this limit? What do I not have? I don't have a common factor. Wait, is that right? Let me check the form real fast. What is the form for my limit? The form for that limit is 2 times 1 minus 3 is negative 1 divided by 1 minus 1 is, oh, that's interesting. What form is that limit taking? The infinite form. I am actually going to get infinity for this limit. Is it going to be plus or minus? Let me do sign analysis. Let's see. We've got negative on the top, and on the bottom, as x goes to 1 from the right, x minus 1 will be positive, so that we end up with negative infinity as the derivative from the right. How the heck did that happen? Let's go back to the graph. What happened was this. we are using h of 1 as one of our points. Here's h of 1 right here. And we are using h of x, for x is close to 1, for our other point. And we are drawing lines that connect the 2 points right there, and then we are letting this point x go to 1. And when we do that, then this line, let me zoom in so you can see what's happening here. We've got a point like this, and we have a hole like this, and here comes our graph, and we are taking points and connecting with lines like this, and as we do so, because the curve is not continuous, those lines are getting steeper and steeper and steeper until when I hit 1, boom, I have to jump down instantaneously, and the only way to do that is with an infinite rate of change.
Why do you draw lines?
Because that's how we compute derivatives. We do a secant line whose slope is the difference quotient. The slope of this line is, this is point, the point is 1h of 1, and this point is h of x. The slope of this line is h of x minus h of 1 over x minus 1.
Wouldn't it be, okay, but that's not how we did limit, was it?
Right. Very good. This is not the limit of the function, it is the limit of the difference quotient, which is why I'm labeling it as a derivative and not the limit of the function. So I want everybody to notice his very good question so we can distinguish between these two things here. The limit as x goes to 1 from the left of h of x is the value that h of x is close to when x is close to but less than 1. Whereas h prime minus of 1 is the value of the slope of h from the left. So this is a function value, and this is a slope. And those two are really different quantities. What is confusing about them is that I compute this guy right here with a limit, but it's not the limit of h, it is the limit of the average rate of change of h. You see it? Okay. Let me state our results for today in the form of a theorem, and then I'll take your question. So here it is. F prime of C exists if and only if F prime from the left and F prime from the right have the same value. And when this occurs, we say that f of x is differentiable at x equals c. And tomorrow we're going to talk more about this idea of differentiable. F prime of c exists if and only if the derivative from the left at c and the derivative from the right at c take the same value. And if that is the case, then f of x is differentiable at x equals c. Joseph, question?
Is it be possible to have the limit as x goes to a form of c equals infinity, and then the derivative be infinity as well?
Yes. Yep. And a good example of that would be the function f of x equals 1 over x at x equals 0. Vertical asymptote and infinite rate of change because my curve keeps getting steeper.
Please explain again, like, f of x is differentiable at x equals c.
This term differentiable just means that the derivative exists.
And the thing, when I said if you can just plug, let's say f x equals 1 into the thing.
Yes.
So it wouldn't work if it's continuous, right?
Okay, yes. Peter has a really good question. And that is, if I happen to know that my function is continuous, can't I just, what you're really doing here when you were plugging in 1 is you are taking the limit as x goes to 1 from the right of f prime of h prime of x.
Maybe left for this case.
Well, left, yes. I'm taking the limit as x goes to 1 from the left of h prime of x. And what I was showing was that that is not the same necessarily as h prime from the left at 1, right? It's not necessarily the same. But if my h prime happens to be continuous, then it will be. Yes.
We have
How are those two not the same?